Let's now see how can we implement the network to solve a regression problem using PyTorch. We will use California housing dataset. Each training example will refer to a house in California, and the input variables represent information about this house, like its size or its location. And then the output value is the price of the house. And the idea here is to try to train the network, like given a number of input variables, for example, the size of the house, the location, how many rooms in the house. This is the features. We call this is the features that describes the house to predict what is the cost of this house. This dataset is not included in PyTorch, so we will import it from scikit-learn. We are going to train with a batch size 128 and for 256 epochs. Then we will import the dataset here using Fetch California. And to separate the data and the targets, we will split it into a training and the test set. We are using here the function from scikit-learn, which is train test split. And we will use 20% for the test dataset, and the rest will be for the training. We need then to convert some of this into the type of the data types that we want to use. So we want to use float 32 because that is what we are using for this model. If we don't do that, we will get an error message later. Then we want to standardize the data. We do this similar to how we did in previous videos, but we use this axis here equals 0 so that we will standardize and have the mean for each feature. So each column will have the mean. And then we create the dataset objects. Now it's time to create the model. We specify the first layer being a linear layer with 8 input. It means 8 neurons, and we have a ReLU activation function, and then the output layer is a linear layer as well. And because it is a regression model, so we will have just a single neuron. To initialize the weights, we use Zephyr initialization, and we do that for the linear layers. We will use the Adam optimizer and the mean squared error as the error function. MSE loss is what we want to use when we do regression problem, and using a linear activation function in the output layer. And here, instead of repeat the training function or the training steps again and again, we used utilities.py file, which we will find it in my Git repo. And this is the utilities class that it has the train model. And if you are using Google Colab to run this code, you have to, first of all, mount the drive, and then to import sys and the import lib. And here you mention your directory to utilities.py if you download from the Git repo. And to do to know where is the utilities, you can here press on this icon and then go to drive, and you can find it. Click, right click on your mouse, and then you can copy the path for the utilities.py and paste it here. Then we import the train model, which has the steps to train the model, as I mentioned here, which we went through this in previous video. And I added here 2 if we want the accuracy for the regression model, we will use the absolute error instead of, we will use the mean absolute error instead of the accuracy. And then we can see here the loss is 0.28. For the validation, it is about 0.29. This trained model, we use it now to predict the value of the cost of the house given the features. So here we will use the test dataset instead of the trained dataset, and we use here the model to have the outputs here, and we can see they are somewhat similar to each other, the prediction and the true value. Let's see how we can modify this version to have better results by using a deeper network. So if you see here the definition of the model, we will use not just 2 layers, but we have this input layer, which is now, instead of 32 neurons, it's 256 neurons. And then we have another hidden layer with 256 neurons. And we use the ReLU, the same as previously. And at the first, when I ran this, I noticed that the train error went down much more than the test error. So this is overfitting. To reduce this, we can use dropout to mitigate this problem. So as you can see here, after finishing the training, let's see, the loss went down to 0.21, about 22. And for the validation, it stopped at 0.24. So we can see that we can get more accurate results by using a deeper network.